we have seen that for M and R module, we get this M tilde, which is an O spec R module. And the first nice observation is that this gives us a geometric interpretation of module theory, because we start with something purely commutative algebra, and then we get this extra structure on this nice topological space with a sheaf of rings. And so because we like this so much, we now want to start restricting to the case where at least locally our OX modules are of this shape. So in other words, if F is a sheaf of OX modules on scheme X, then we say it is quasi-coherent if there exists an affine open cover of X by the spec Ri, such that on each cover, on each element of the cover, if we restrict F to this Ui, then it is isomorphic to this sheaf Mi tilde for some Ri module Mi. So locally, we are exactly of this shape. Some remarks. Actually, this is one of these situations where if this property holds on some affine open cover, it actually holds on all affine open covers. In particular, if F is quasi-coherent on X and U is any affine open subset of X, then restricted to U, F is of this form M tilde, and we can actually see what M has to be, because taking the sections on U must give us back this M. So in other words, this M is just the sections of F on this affine set U. This is something we're not going to show, but if you're interested in the proof, you can look at Hartshorn's book on algebraic geometry. This is proven in this proposition here. The second, there is a kind of stronger version of this definition, which is that F is a coherent sheaf if not only it has these properties, but in fact these Mi are finitely generated Ri modules above. So we're not going to need this so much, though we're going to see a hint of where this property comes in. But if you continue with the study of sheaves, then this is a property that you're going to use a lot. Okay, to see at least some few examples, when X is any scheme, then F equals OX is quasi-coherent. It's in fact coherent because then on any spec Ri, well, just take Mi to be Ri, then, well, this restriction of the structure sheaf gives you O spec Ri, and we have seen this is just isomorphic to this sheaf associated to Ri itself. So this has this nice property, at least the structure sheaf is on our side. And then, for example, on Pn, we constructed by hand these OPND, these twisting sheaves, and these are also quasi-coherent because we have seen that on this standard affine open cover Ui of Pn, this restriction here is isomorphic to OUI, which is again by part A, is of the correct shape, like this. So also this is an example that we have already seen. And next, what we're going to do, the big content of the video, is that everything we can do with modules, quasi-coherent sheaves also do, and they respect what the modules did for them. And so this lemma is formulated on an affine scheme where we see that all the constructions of OX modules that we know are compatible with the constructions of modules over R that we like. So for part A, if you have two R modules, M and N, then there's a bijection between the morphisms of OX modules between the associated sheaves and the R module homomorphisms from M to N. There's a bijective thing, so in particular, we understand what are the morphisms between these associated sheaves. Then we talked about exact sequences, and the sequence of R modules is exact if and only if the corresponding sequence of their OX modules is exact. Note here, we already use part A to write this down, right? Because, for example, here we have this morphism of R modules, and so by part A, we get an induced morphism of the sheaves. So this is why this even makes sense. And then finally, so this was about this exactness. There were also the more direct hands-on constructions with modules. like direct sum, tensor product, and dual. And again, here the lemma says that, for example, the direct sum of the tilde sheaves is just the tilde sheaf of the direct sum of modules. Similarly, tensor product. And here for the dual, this works when M is a finitely generated R module over an Noetherian ring R. So two finiteness assumptions here. And at least we see one example where it's kind of nice to have this module being finitely generated. And then the final conclusion of the lemma is, from these properties, in fact, it follows that if you have a map between quasi-coherent sheaves, then the kernel, the image, and then also quotients, direct sums, and tensor products of these quasi-coherent sheaves are still quasi-coherent. So somehow once we're in this land of quasi-coherent sheaves, we stay in there with all the constructions that we have seen. Okay, so for the proof, for part A, we need to have a bijection between these two sides. So we start on one side and try to go to the other. The easy direction is going from left to right. If you have M tilde mapping to N tilde as an OX module, then we want to go from M to N. We can do this by just taking global sections. Because we have seen the global sections of M tilde are just M. The global sections of N tilde are just N. So if we start with F tilde, we get this F. And this is not just some map, but in fact, it's a homomorphism of modules over OX of X, so also global functions. But we have seen this is just R. So one direction we already went from F tilde to F. Conversely, well, if you have such a morphism of R modules, now we want to go to this here. And if you recall the sections here, they are collections of elements in the localizations of these at the prime ideals P. And where we do get from a map of R modules, we get the corresponding map of the localizations for all primes in R, so for all points in spec R. And then these things, so if you start with a section here, which is a collection of elements in these MPs having a nice form, then you apply this, you get a collection of elements in NP, you verify it still has the nice form that you want. And so what this tells you is how to go from a section of M tilde to a section of N tilde. These fit together to give you such a morphism, and you just check these constructions. Both are inverse to each other. So this gives the two bijections that we want. The second one was about exactness of sequences. So we start with a sequence of modules over R, and then we say this is exact if and only if where we want to place these tildes everywhere. And the first observation is, again, we need to go via the localizations. And the first observation is that this exactness is equivalent to saying that the corresponding sequence of localizations is exact at all prime ideals. And this was proven in, so this equivalence here, this is purely commutative algebra statement, and this was proven in Gatman, his script on commutative algebra, and proposition 6.27. And now we're in good shape because, as already indicated, these are the stalks of the mi tilde at P. And so, well, we want to check the exactness of this. 0 goes to M1 tilde, goes to M2 tilde, goes to M3 tilde. goes to 0, we want to show this is exact. In fact, we want that this is an equivalence. But now we know that this sequence here gives us an exact sequence of the stalks at all primes. And so by this lemma 13.21 in the algebraic geometry script, the exactness of this sequence here can be checked. And in fact is equivalent to the exactness at the stalks. So here we see a more general pattern where two theories work very nicely together. We have the theory of these sheaves of modules, and there a lot of things like being an isomorphism to maps agreeing can be checked at stalks. On the other hand, we have commutative algebra and a theory of modules, where a lot of things, again, being isomorphism and so on, can be checked at stalks at all, or can be checked at all the localizations at all prime ideals. And because the stalks on one side correspond to the localizations on the other side, then this transfers a whole range of results from one theory to the other, as we're currently doing. Okay, this was about exactness. And then finally, we also want to see that these direct commutative algebra constructions are compatible. And again, a purely commutative algebra statement is that the direct sum and tensor product commute with localization, and then taking the dual commutes with localization when you are in the situation that you have a finitely generated module over an Euclidean ring, which is exactly why we ask these properties above. And then, for example, if you want to check this statement here, that taking direct sum commutes with taking the tilde operation, what we just do is we construct a morphism from this sheaf to the other sheaf, and then we can conclude it's an isomorphism by checking it at stalks, and then we're in good shape. So we want to go from one side to the other side. We just have to see when U inside X is open, we need to start with a section on one side and land on the other side. So somehow a section of this here on U is just a section of M tilde on U, a section of N tilde on U. And these are given by these collections of elements in the stalks. This is a section here where it's phi p in this localization, the psi p in this localization. And then where we need to land at a section here, and what are we going to do? We just take this collection of phi p direct sum psi p. We claim this is the section of M direct sum N tilde on U. So a priori, this here, this direct sum is just an element of, well, you have one thing in one side and one thing in the other side. But then this here, this equivalence is exactly this lemma here, direct sum commutes with localization. This is equivalent to M direct sum N and then localize. But you see now we have a section of localizations of this module at various points. These fit together nicely. Again, this is something you can check yourself. And so they give a section here. And so we have constructed with this now this morphism from M tilde direct sum N tilde to this way around. So we have a morphism, and it's also a morphism of OX modules. And well, we just defined it using the stalks, and then in fact it is an isomorphism of stalks at P. This is essentially this isomorphism here, because this here is the stalk of this sheaf at P, and this is the stalk of this sheaf at P. And so having a morphism which is an isomorphism at stalks, again, shows it's an isomorphism of OX modules. Okay, and then, so let's see. Last thing that we want to show is that, that, for example, if we take a kernel of a map of quasi-coherent sheaves, then this is again quasi-coherent. Okay. So for this, let's say if F and G are quasi-coherent modules and they have morphism between them, like this, then, well, we want to check that if you take the kernel sheaf and restrict it to any open affine subset or somehow some nice collection of these, then you're again quasi-coherent. Then you're again one of these tilde sheaves. And so let's give ourselves U equals spec R inside X open. Then there we have, so here we use this kind of assumption that was proven in Hartshorne that we don't do ourselves, that this restriction is isomorphic to some M tilde, and G restricted on there is isomorphic to some N tilde. This is where we use that they are quasi-coherent themselves. And, well, of course, this restricted morphism gives us a morphism of the restrictions. And then, so somehow here we get a morphism from M tilde to N tilde. So by part A that we proved above, we have that there's a corresponding map, which is an R module homomorphism. Okay. And so we can write down a short exact sequence, namely the kernel of this, sorry, this, to give it a new name, maybe we should call this big F. And then the kernel of this big F, by definition, sits inside some exact sequence like this, exact sequence of R modules. And then by part B, we get a corresponding exact sequence of the tilde things. But now we see this here is F restricted to U, this here is G restricted to U, and this is the corresponding restriction here. And so by definition, this here is the kernel of this map. This is basically the definition of this sequence of sheaves being exact. So somehow this here, first of all, is the kernel of F restricted to U, because this here is F restricted to U. And while taking the kernel commutes with taking restrictions, because somehow you just define the kernel to be the thing on each open subset. So this is also the same as the kernel of F restricted to U. And so we see this sheaf kernel of F, if we restrict it to this affine open subset, then it's given by one of these tilde modules, and this is just the definition of kernel F being quasi-coherent. And so this was the thing for kernels, and then images and all the other things work similar. Okay, so this was kind of a big technical lemma, but the good thing now, what it allows us to do is, well, all of these constructions of OX modules in general, they were pretty complicated, right? Even kind of taking a tensor product, we first had to take the pre-sheaf, then sheafify, which was a kind of strange operation. And what this tells us is that if we restrict to quasi-coherent sheaves, then, for example, if you want to take a tensor product, we know what to do because we just look at what the corresponding modules are, take the tensor product of modules, which we understand pretty well, take the associated sheaf. So this here allows us to do all of these local computations purely in the realm of commutative algebra. This is why working with quasi-coherent sheaves in general is nicer and more manageable than working with arbitrary sheaves. So this is everything about this technical statement, and we'll continue studying these quasi-coherent sheaves for the rest of the chapter.